Hello, I'm Anish. Today I'll be talking about neural networks, but in a less familiar way than what you're probably used to. We'll be building a neural network in Python, but using only NumPy. We'll train it to map certain inputs to certain outputs. This video aims to build a mechanistic understanding of neural networks, showing what mechanisms enable them to create input-output mappings and how this tool is so powerful. For this video, you'll need to conceptually understand neural networks and their basic components. Units, connections, and activations are not explained in this video. You'll also need to understand the concept of vectors and matrices and matrix multiplication. You should have some familiarity with neural networks before watching this video. Let's start by defining what it means to build an input-output mapping. Given a set of inputs and a desired output for each input, can we develop a network that maps each input to its desired output? Let's design our network to solve a problem so that we can evaluate its performance. After all, our numbers need to mean something. Let's provide our network with a binary list of 9 items for input. Our network should identify the majority item in the list, in this case either a 1 or a 0. We'll assume that the input units are directly representative of this. If the input unit has an activation of 1, then that means the list item is 1. And if the input unit has an activation of 0, the list item is 0. Thus, this binary list is basically just a list of the activations in the input layer. Let's start by actually defining the inputs and outputs which we want to make mappings of. We'll start by making 2 variables, one for the inputs and one for the desired output, and we'll define 4 examples for each, creating 4 input-output pairs. Now that we've constructed our data, let's begin to set up the network. Our network will have 9 input units and 1 output unit, where every input unit is connected to the output unit. We'll provide input into our network in the form of a 9x1 vector, with each element to represent the activation value of each input unit. We'll store the connection weights in a 1x9 vector, or matrix. Each element will represent the strength of each input unit's connection to the output unit. We'll create a similar 1x9 matrix delta to store how our weights change in each training cycle. This will be covered a little bit more later. We're almost done setting up the network. We've set up all the components. Now we just need to define how the weights will change, or how our network will learn. There are a ton of learning algorithms out there, which you've probably heard of, but we're going to focus on a simple mechanistic understanding of how a network learns. Instead of focusing on a specific algorithm, our approach will focus on an intuitive principle you use every day: learning from your mistakes, also called error correction. For now, let's assume we have a network. Let's not focus on the actual values of our weights and activations, just the concepts for now. If we make a prediction, and this prediction is wrong, we want to have our network learn from this incorrect prediction. Our weights contain what our network knows, so changing the weights effectively changes what our network knows. How should we change this weights to improve what our network knows? To think about this, let's consider 2 scenarios. I forget to write this down on the whiteboard until later, but we calculate the error as the desired value minus the predicted value, and this becomes clear why later. Consider the case in which the desired value is 0 and our network predicts 0.6. The network overshoots its guess. The predicted value is greater than the expected value. When we compute the error will be negative. Consider the opposite scenario, where the network undershoots the guess, where the predicted value is less than the expected value. Let's let our desired value be 1, and our network predicts 0.3. Remember, these values are arbitrary, but they're realistic guesses for an untrained network. Let's look at the scenarios again. In our network, the output activation is computed as a weighted sum of the input. In the first scenario, if our weights were lower, our predicted value would have been lower, and therefore more accurate. Similarly, in the second scenario, if our weights were higher, our predicted value would have been higher and more accurate. From this, we can see that if we move our weights in the direction of the error, next time we guess, the guess is going to be more accurate. But this introduces another question. How much should we move those weights? We don't want to just consider how wrong we are, but we also want to consider how much influence each weight has on the output. If our weight is not affecting the output, why change it? For any network guess, the input units that influence the guess most are the ones with the highest activation. If the input value is higher, then it has a larger contribution to the output, since the output is computed as a weighted sum. When we want to nudge our weights, we'll want to consider both of these. How wrong is our guess, and how influential is each input, and by extension each weight, is in making this prediction. Let's look at the process for changing the weights. For each weight, we'll change the weight in proportion to the input activation correlated with that weight and the error. We'll change the weights by a small proportion of these, called epsilon. Epsilon is interpreted as our learning rate, and it's commonly set to a value of 0.01. We'll apply this process once per weight for each weight for 1,000 training cycles. After learning about it conceptually, implementing the code is pretty simple. We'll iterate over each input, multiply the activation by the error and our learning rate, and then we'll store that in delta. Then we'll add delta to our weights. Instead of using the delta list, you could add these values to the weights directly, but I like to use delta for organization purposes. Now we've written basically all the code that defines our network. Now all that's left to do is train the network on our inputs and test it. One of the reasons we stuck with such a basic network is for interpretability. We built this network to study how neural networks create such mappings. One of the most straightforward things to do at this point is to look at the weights of our network. This is a technique called weight inspection. What is the network actually doing to these inputs that makes them reach the desired output? In our example, majority rule, every input has an equal impact on the output. The problem involves counting the inputs, and when you count, no item is more important than another item. You're just counting. Since we know this, then we can see that all of our weights should be equal, or at least somewhat equal. If our weights should be uniform, then why are they not? Let's modify the data to be more representative of a majority rule problem. Earlier, we explicitly defined 4 examples. We have 9 inputs, each with 2 possible combinations. That means we have 2 to the power of 9, or 512 possible scenarios. We only trained on 4 of these. That's about 0.7% coverage. We know our network is able to generate these correct predictions for inputs that it was explicitly trained on. But what about on an input we haven't seen before? Let's quickly write some code to generate 10 random inputs and make guesses. We can see that these guesses are not really consistent with solving the majority rule problem. Sometimes they are, but even with a random guess, it's still a 50-50 chance. Our network still fails to solve the problem. Let's revisit our training data. Let's iterate through all 512 possible combinations of the majority rule problem and train on all of the examples. If we look at the weights are more uniform, but they're still not exactly uniform. More importantly, our network generates incorrect predictions, even for examples that it was explicitly trained on. What's stopping our network from pairing these inputs with outputs? Or AKA, what's stopping our network for generating these input-output mappings? To solve our issue, let's head back to the whiteboard and think about what our network is doing, and what it needs to do to solve the majority rule problem. For now, let's examine a network more suited to solve this problem. One with uniform weights with arbitrary values, let's say 1. We'll choose 1 so it's easy to work with. Let's consider an example where we give this network an input of 5 ones and 4 zeros. In this case, the desired output is 1. In this new network, our weighted sum for the output unit is 5. Our network is adding up the inputs, but it's not able to declare a threshold for this sum. We need to give our network the ability to sort of analyze this sum. Let's see what happens when we subtract a constant value. In this case, let's choose 4. By choosing 4, we're able to declare 5 as a threshold for when the output activation will be 1. If the sum is less than 5 and we subtract 4 from it, our output activation will be less than or equal to 0, not 1. If our output activation is 5 or more and we subtract 4 from it, then we'll get the expected value of 1. We can see that this constant value we added acts as a threshold for our network. This value is called a bias. This bias is learned along with the weights, also following the error correction principle. This is where we start to see an underlying structure in this network. Let's add in the bias to our activation equation. If you look at this equation, you can see it's essentially taking a specific set of 9 inputs and transforming it with the weights and bias to produce an output. The weights scale the input, and the bias shifts it. This essentially describes the network as a function, where the bias is the intercept, or the constant term of our function. If you remember your algebra, a function is what maps inputs to outputs. Neural networks essentially operate as functions, where these functions are approximated from the training data during the training process. Let's look at how to implement a bias in our code. We'll simply introduce a new variable for the bias, and we'll calculate it similarly to how we calculated the error, and we'll then introduce this constant term into our calculation of the activation of the output unit. Let's train and test our network again to see how the bias impacted things. Let's look at the weights and bias in our network. We have uniform weights, all of value 1, and a bias of -4. This is expected from our analysis on the whiteboard. We can see now that our network does explicitly map every single input to every single output. Our network generated these mappings on all 512 inputs of training data. Alternatively, you could train on a smaller portion of these 512 combinations. In that case, the trained combinations would be explicit mappings, while the untrained combinations would be implicit mappings. It's important to recognize that our network is predicting values which are greater than 1 and less than -1. Typically, we interpret these values truncated at -1 and 1. In this video, we looked at creating input-output mappings using neural networks. And we saw that essentially what we're doing is we're approximating a function of the training data. We learned that neural networks operate as mathematical functions, mapping these inputs to outputs. We touched on the importance of interpretability, and we talked about weight inspection as a technique to study how a network is solving the problem it's solving. Unexpectedly, weight inspection helped us discover the importance of adding a bias in these networks. Neural networks are fundamentally based on the brain. If a bias is not a unit or a connection in our network, then what is it with respect to the human brain? In biological neurons, the concept of a bias or a threshold is inherent. A brain neuron requires a certain level of stimulation before it starts to fire, where that level of stimulation is determined by biological and physical properties. In our simulated artificial neural networks, we introduce the bias to explicitly simulate this effect. This is an example of why it's important to recognize that artificial neural networks simulate the brain, but we can see that they're still fundamentally a little different. In a future video, I'll talk more about biologically plausible neural networks and how this might be an alternative path forward for the field of AI. Thanks for watching.